Given the function f of x is equal to x cubed minus 4x squared minus 5x minus 3, and then we're told to compare this graphically to the parent function, which is x cubed. So when we talk about modeling data, essentially what we do in the real world with math is usually we have data. So I go out and I measure something, and it doesn't matter what I measure, but I compare that something, and I measure lots of data. And so I compare two variables and I plot the points. And if I plot the points and I get a shape that looks like this, I want a mathematical equation, right? And so when I want a mathematical equation so I can predict things that happen. So I don't know what this data represents. Maybe it represents like your education level and your salary, or maybe it represents the number of hours you study and your grade performance. It can measure anything, but I'm comparing two variables where I believe that one variable is dependent upon the other. In other words, you might make the assumption that the more that you study, the better your grade will be. Or the higher your education, the more salary you'll earn. You would assume that. Well, the independent variable was x, and the one that's dependent upon the value of x is the dependent variable. And so if I plot those points and I get a shape, I want to make a mathematical model so I can make predictions. And so the reason we teach you guys all of these equations is so you should be able to look at this and say, you know what, that looks like a cubic. And so, you know, it's going to be, you know, f of x, some variation of x cubed. But it won't be perfect. We have to shift it up and down. We have to stretch it. We have to move it left and right. And so that's what we're going to focus on today. And so what we've been asked to do is we were asked to graph g of x. This is what example number 3 wants us to do, is we're asked to graph g of x. So I'm going to do that. I'm going to come in here and I'm going to say x cubed, because that's what g of x is. And we'll just do a standard view like this. For the most part, looks pretty common, right? Then we're asked to graph the other function, which is a little more difficult. Well, not difficult, but it has a lot more terms. So we're asked to graph x cubed minus 4x squared minus 5x minus 3. Now before I hit the graph button, what's the big difference between the two? Well, we got to look at all the details, right? They're both third degree polynomials. They both have a leading coefficient of 1. And then after that, there's a couple of other little things, like the second one has an x squared and an x and a minus 3 and stuff. And I would suspect that that has something to do with the shifting left to right, moving up and down. But we're not stretching it vertically, we're not shrinking it vertically, because the leading coefficient is what does that. And so what we do then is we just look at the graph. Wow. That's different, right? So if I zoom out just a little bit, you could see a radical difference between the two, right? So let's zoom in. They show the windows. If I go from negative 56, so in your textbook what they do is they go from negative 56 to 56, and then in the y direction, and this is interesting, they go from negative 12,000 to 12,000. Oh, I got one too many zeros there. Now when you look at it that way, they look pretty much the same, don't they? You can't see that much of a difference. But if I go to a standard zoom, radically different. So if I had data that look like this, I would have x cubed. But what if I went and I measured data that look like this? I would need an equation that's more like this, right? So what are they trying to tell us? Well, there's a couple things that we need to notice that are the same. They're both odd powered or odd degree functions. So that means they come in from one side and go out the other. In other words, they come in from the bottom and go out the top. If I were to flip that leading coefficient to a negative sign, they would come in from the top and go out the bottom. And the limit as they approach infinity in the x direction is infinite, right? So let's write that down. Let's write some of this stuff down. So the limit of f of x as x approaches infinity is equal to the limit of g of x as x approaches infinity, which is infinity. The limit of f of x as x approaches negative infinity is the same for g of x, which is negative infinity. Now what that means is if I pick either one of these equations and I move my cursor towards negative infinity in the x direction, what does my y value approach? Negative infinity. If I kept doing this, that y value just keeps getting more and more negative. So over time, I'll approach infinity. Now if I go the other direction, if I come back the other direction and I approach positive infinity in the x direction, what you'll see is that my y value starts to get bigger. And if I keep going, as x increases, what does y do? It increases. So as long as x is increasing, y will continue to increase. So as x approaches infinity, then my y value approaches infinity. Does that make sense? Now, why is that? Well, because they're both third degree polynomials, because they both have a leading coefficient of 1, so they have the same leading coefficient, so the end behaviors are the same, but the only thing that's different is the middle. And the reason the middle is a little different is because of this. This behavior pretty much remains the same as you approach infinity or negative infinity. Only thing that changes is the stuff on the inside, and that's due to this. And that's all they wanted you to see. Does that make sense? Yes, mister.